Deep reinforcement learning, deep RL, research faces significant challenges in scaling environment simulations, hindering rapid experimentation and progress. Most existing environments, including MiniGrid, struggle with CPU-bound limitations, resulting in slower computation and communication overhead when distributing tasks across multiple machines. This bottleneck severely impacts training speed and throughput. To address this issue, the authors introduce NAVIX, a reimplementation of MiniGrid in JAX, which achieves over 200,000 times speed improvements in batch mode, supporting up to 2048 agents in parallel on a single Nvidia A100 8.0 This remarkable scaling ability reduces experiment times from 1 week to 15 minutes, fostering faster design iterations and more scalable RL model development. The authors highlight the importance of efficient environment implementations, citing the notorious sample inefficiency of deep RL, which often requires between 10 to the power of 7 to 10 to the power of 9 interactions for training. While agent solutions have improved significantly in recent years, environments have not kept pace, relying on CPU-based implementations that cannot adapt to different devices and require complex distributed systems. NAVIX bridges this gap by leveraging JAX's intermediate language representation to migrate computation to different accelerators, such as GPUs and TPUs. The authors demonstrate NAVIX's scalability by training over 2048 PPO agents in parallel, each using their own subset of environments, all on a single Nvidia A100 8.0 The main contributions of this work include a fully JAX-based implementation of environment configurations that reproduces exactly the original MiniGrid Markov decision processes, MDPs, and partially observable MDPs, POMDPs, a description of the design philosophy and principles of NAVIX, and a set of RL algorithm baselines for all environments. This work builds upon the growing trend of JAX-based environments and frameworks, which propose batched implementations of common RL environments to increase speed and throughput. The paper discusses the development of NAVIX, a JAX-based re-implementation of the popular MiniGrid suite for deep reinforcement learning experiments. NAVIX aims to provide a full, batched, and fully jittable version of the MiniGrid environments, allowing for the training of thousands of agents in parallel on a single accelerator. This is achieved through the use of the Entity Component System Model, ECSM, a design pattern widely used in video game development, which allows for easy generation and extension of tasks. NAVIX environments can be compiled into XLA and run on any JAX-supported accelerator, including GPUs and TPUs. The environments are designed to exactly match MiniGrid in terms of environments, observations, state transitions, rewards, and actions, making it a drop-in replacement for the original environments. The design principles underlying NAVIX include matching the original MiniGrid suite and ensuring that every environment is fully jittable and differentiable, aligning with JAX requirements. The paper also highlights the importance of a stateful computation for environments to be fully jittable, which requires defining an environment state object called the timestep. This structure is necessary to guarantee the same return schema for both the step and reset methods, allowing the environment to auto-reset and avoiding conditional statements in the agent code that would prevent the environment from being fully jittable. In addition, the paper addresses the limitations of the original MiniGrid reward function, which is non-Markovian due to its dependency on the number of steps taken by the agent to reach the goal. NAVIX departs from this function and uses a Markovian reward function instead, which is 0 everywhere and 1 at task completion. This change may call into question the validity of historical results obtained with MiniGrid and the generalization of these results to other environments. The agent interacts with the environment using the "step" method, which takes the current time step and action as input, and returns a new state of the environment. The agent can also sample a starting state from the starting distribution "P0" using the "reset" method. The environment is designed to be stateful, with an explicit random key used for the stateful random number generator. The NAVIX environment is implemented using the JAX library, which allows for just-in-time (JIT) compilation of the environment interactions. This results in significant speed improvements compared to the original MiniGrid implementation. The environment is also designed to be flexible and extensible, with a modular architecture that allows for easy addition of new environments, observations, rewards, and termination functions. The Entity Component System Manager (ECSM) architecture is used to manage the state of the environment. Entities, such as the player, walls, and keys, are composed of components that hold the data of the entity. Systems, such as the intervention, transition, rewards, and termination functions, operate on the collective state of all entities and components. The components in NAVIX provide properties that hold the data that can be accessed and manipulated by the systems. These properties include position, direction, color, probability, and more. The entities in NAVIX are characterized by the components that they possess, and the systems that operate on these components provide the observations, rewards, and state transitions. The NAVIX environment is designed to be fast and efficient, with a focus on speed and throughput. The environment is benchmarked against the original MiniGrid implementation, and results show that NAVIX is over 45x faster on average. The improvements are due to the migration of the computation to the GPU via XLA, and the use of JIT compilation. The NAVIX environment is also designed to be flexible and extensible, with a modular architecture that allows for easy addition of new environments, observations, rewards, and termination functions. The environment is designed to be useful for a wide range of reinforcement learning tasks, and provides a set of baselines for all environments. Here is a combined summary of pages 7 and 8. The authors evaluate the performance of NAVIX, a novel implementation of the MiniGrid environment, in terms of speedup and throughput. Figure 3 shows the speedup of NAVIX compared to the original MiniGrid implementation across various environments, demonstrating a significant improvement. To further investigate the speedup, the authors vary the number of training steps and observe that NAVIX consistently outperforms the original implementation, regardless of the number of steps, figure 4. The authors then examine the throughput of NAVIX by measuring the computation time while varying the number of environments running in parallel. NAVIX utilizes JAX's native VMAP, which directly vectorizes the computation, allowing it to scale up to 221 environments in parallel, whereas the original MiniGrid implementation is limited to 16 environments due to memory constraints, figure 5. This results in a throughput over 10 to the power of 5 times higher than the original implementation. Furthermore, the authors simulate training multiple PPO agents in parallel, each with their own subset of environments. NAVIX achieves a significant speedup, training 2048 agents in less than 50 seconds, whereas the original implementation takes around 240 seconds to train a single agent, figure 6. This translates to a speedup of over 200,000 times. The authors also provide additional baselines using implementations of PPO, double DQN, and soft actor critic in ReJAX, optimizing hyperparameters for each algorithm and environment combination using random search. The hyperparameters are evaluated across 16 different initial seeds, and the configuration with the highest average final return is selected. The baselines are run for 10 million steps across 32 seeds, with the tuned hyperparameters for the environments shown in figure 7. The NAVIX Environment Suite, a re-implementation of MiniGrid in JAX, leverages JAX's intermediate language representation to migrate computation to different accelerators, such as GPUs and TPUs. This design philosophy, pattern, and organization are highlighted, showcasing connections to the ECSM design pattern and correspondence between function structure and mathematical formalism of reinforcement learning, RL. The environment interface, available environments, and scoreboard storing state-of-the-art results are presented, allowing new algorithms to refer to and avoid running baselines prone to errors and manipulations. NAVIX demonstrates significant speed improvements over the original MiniGrid implementation, with a 1000x increase in speed, reducing 1-week experiments to 15-minute ones. This scalability is crucial for keeping up with the state-of-the-art in RL research and developing new, more efficient algorithms. The ability to run fast experiments is vital for the RL community, and NAVIX aims to foster the development of new algorithms and exploration of new research directions. The references provided include various papers and libraries related to RL, such as model-based RL for Atari, meta-RL agents, and differentiable physics engines. These references highlight the connections between NAVIX and existing work in the field, showcasing the broader context and relevance of the research. Libraries such as TensorFlow, PyTorch, and JAX are also mentioned, demonstrating the use of these tools in the development of NAVIX. Figure 7 presents episodic returns for a sample of NAVIX environments for DDQN, PPO, and SAC baselines, with lines representing averages over 32 seeds and shaded areas showing 595 percentile confidence intervals. This figure demonstrates the performance of NAVIX in various environments, highlighting its capabilities and potential applications. Overall, NAVIX offers a valuable tool for the RL community, providing a scalable and efficient environment suite for developing and testing new algorithms. Its connections to existing work and libraries demonstrate its relevance and potential impact on the field. Reinforcement learning environments are crucial for developing and testing agents. Recent advancements have led to the creation of various environments, including NVPool, PGX, JAXMarl, XLand MiniGrid, CraftTax, and Jumanji. These environments are designed to facilitate parallel execution, scalability, and flexibility, enabling the development of more sophisticated reinforcement learning algorithms. Several research papers have focused on improving exploration in reinforcement learning. For instance, the paper, Ranked the Episodes, a simple approach for exploration in procedurally generated environments, proposes a method for ranking episodes to encourage exploration. Another paper, How to Stay Curious While Avoiding Noisy TVs Using Aleatoric Uncertainty Estimation, introduces an approach for estimating uncertainty to avoid noisy TV states. In addition to exploration, researchers have investigated various techniques to improve reinforcement learning. The paper, Prioritized Level Replay, presents a method for prioritizing level replay to accelerate learning. A consciousness-inspired planning agent for model-based reinforcement learning proposes a planning agent that leverages a consciousness-inspired approach. History compression via language models in reinforcement learning demonstrates the application of language models for compressing history in reinforcement learning. Other papers have explored the use of approximate symbolic models, adversarial guidance, and language abstractions to improve reinforcement learning. The paper, Leveraging Approximate Symbolic Models for Reinforcement Learning via Skill Diversity, investigates the use of approximate symbolic models for skill diversity. Adversarially Guided Actor Critic proposes an adversarial approach for guiding actor-critic methods. Improving intrinsic exploration with language abstractions demonstrates the effectiveness of language abstractions for intrinsic exploration. The Muhoko physics engine and OpenAI GIM have been widely used in reinforcement learning research. More recent benchmarking environments, such as Minotaur, PopGIM, and benchmarking the spectrum of agent capabilities, have been developed to provide a more comprehensive evaluation of reinforcement learning algorithms. These environments, along with the aforementioned research papers, have contributed significantly to the advancement of reinforcement learning research. The soft actor-critic algorithm, introduced by Harnoya et al. 2018, is a maximum entropy deep reinforcement learning method that utilizes a stochastic actor. This algorithm is employed in the NAVIX framework, which is designed to maintain a bijective relationship between systems and their mathematical formalism in reinforcement learning, RL. This relationship enables seamless translation between mathematical formalism and code implementation. In NAVIX, systems are functions that operate on the collective state of all entities, defining the rules of interactions between them. The framework includes 5 primary systems: intervention, transition, observation, reward, and termination. The intervention system is a function I s times a right-pointing arrow s that updates the state of entities according to actions taken by agents, corresponding to the canonical decision in an MDP. The transition system is a function micro s times a right-pointing arrow s that updates the state of entities according to MDP state transitions, corresponding to the canonical state transition kernel in an MDP. The observation system is a function O s right-pointing arrow O that generates observations for agents, with multiple observation functions available, including first-person, top-down, and third-person views in symbolic and pixel formats. Both full and partial observations are provided, allowing NAVIX environments to be cast as either MDPs or POMDPs. The reward system is a function R s times a right-pointing arrow R that computes rewards for agents, while the termination system is a function gamma s right-pointing arrow 0, 1 that determines episode termination. Both systems rely on the concept of events, representing goals to achieve. Reusable patterns are also provided in NAVIX, including examples of how to JIT the full interaction loop of a NAVIX environment and run multiple seeds in parallel. Additional examples, such as JITing a whole training loop with a JAX-based agent and automating hyperparameter search, are available in the NAVIX documentation. Tables 4, 5, and 6 summarize the implemented systems in NAVIX for observation, reward, and termination, respectively. The paper discusses the implementation of various functions in the NAVIX environment, a highly customizable platform for creating new environments by combining existing entities and systems. It begins with an overview of observation functions, which include symbolic _first_person, RGB, RGB_first_person, categorical, and categorical_first_person. These functions are designed to provide different views of the environment, such as canonical grid encoding, first-person views, and entity ID grids. The reward functions are also detailed, including on_goal_reached, on_lava_fall, on_door_done, free, action_cost, and time_cost. These rewards incentivize or penalize the agent based on its actions and outcomes, like reaching a goal or falling into lava. Termination functions are presented as well, which terminate the environment under certain conditions, such as when a goal is reached, lava falls, or a door is done with the correct color specific in the mission. The paper then moves on to demonstrate how to use NAVIX in practice. Code examples are provided for JITting full interaction loops and running multiple seeds in parallel. JITting the step function allows for faster computation, while running multiple seeds in parallel can significantly speed up experiments. Finally, the paper highlights the customizability of NAVIX environments, showcasing how users can create new environments by combining existing entities and systems. An example is given where the agent must reach a goal while avoiding lava, combining the goal and lava entities with the reward system. This flexibility makes NAVIX a versatile tool for researchers and developers working on various AI and machine learning projects. NAVIX, a modular and extensible environment for reinforcement learning, is designed to facilitate the creation of complex environments by combining different systems. To create a NAVIX empty 5x5v0 environment with a custom reward function, the --NX rewards compose function is used to combine multiple reward functions, such as on_goal_reached and on_lava_fall . This is demonstrated in code 4. The reward_fn parameter is then passed to the --NX make function to create the environment. Alternatively, a custom observation function can be used by passing the observation_fn parameter to --NX make as shown in code 5. This allows for the use of different observation functions, such as --NX observations.rgb . The termination_fn parameter can also be used to customize the termination function, as demonstrated in code 6. NAVIX is designed to be extensible, allowing users to create new entities, components, systems, and environments by implementing the necessary functions. Templates for extending NAVIX environments are provided, including code 7, which shows how to create a custom environment by defining a --reset function and registering the environment with --NX registry. Register_env . Code 8 demonstrates how to create a custom component by defining a new class that inherits from --NX component and specifying a custom property with a type annotation and shape. Code 9 shows how to create a custom entity by defining a new class that inherits from "(NX) entity" and implementing 4 required properties: "(walkable), "transparent", "sprite", and "tag". These examples illustrate the flexibility and customizability of NAVIX, allowing users to create complex environments and entities by combining different systems and components. By providing templates for extension, NAVIX enables users to easily create new environments and entities, facilitating research and development in reinforcement learning. Here is a combined summary of the 2 pages. The code snippet provided in Code 10 demonstrates how to extend NAVIX by creating custom systems. It defines 5 functions: "my_reward_function", "my_termination_function", "my_observation_function", "my_intervention_function", and "my_transition_function". These functions are essential components in defining a custom system within NAVIX. The reward function assigns a reward to each state action pair. The termination function determines when an episode terminates, the observation function specifies the observation space, the intervention function applies an intervention to the system, and the transition function updates the system state. Figure 8 presents an ablation study, comparing the speedup of NAVIX to the original MiniGrid implementation without batching. The results show that NAVIX achieves significant speedup across various environments, as indicated by the lower values on the y-axis. The z-axis corresponds to the environment IDs, which are listed in Table 7. Table 7 provides a comprehensive list of environments available in NAVIX, along with their corresponding IDs. The table includes a diverse range of environments, such as empty grids, dorky environments, 4 rooms environments, and dynamic obstacle environments. This extensive collection of environments enables researchers to evaluate their algorithms in various settings. The environments listed in Table 7 are used in the ablation study presented in Figure 8. By providing this table, the authors facilitate reproducibility and enable researchers to easily identify and select environments for their experiments. Overall, the code snippet, figure, and table demonstrate the flexibility and customizability of NAVIX, as well as its ability to accelerate research in the field of reinforcement learning. The research paper presents a comprehensive list of environments available in the NAVIX platform, a suite of navigation tasks designed to evaluate the performance of reinforcement learning algorithms. Table 8 outlines the various environments, including their unique identifiers, class types, height, width, and reward functions. The reward functions, denoted as R1, R2, and R3, are defined as follows. R1 is a goal achievement reward, R2 is a goal achievement and lava avoidance reward, and R3 is a goal achievement and dynamic obstacles avoidance reward. All environments terminate when the reward is non-zero, such as on goal achievement or lava collision. The paper also provides details on the hyperparameters used for the baseline algorithms, including proximal policy optimization, PPO, deep Q networks, DQN, and soft actor critic, SAC. Table 9 lists the fitted hyperparameters for each algorithm, including the number of environments, steps, epochs, mini-batches, discount factor, and other relevant parameters. The hyperparameter settings for each environment and algorithm are available online. The reward functions and environment settings are designed to challenge reinforcement learning algorithms in various ways, such as goal achievement, obstacle avoidance, and dynamic environments. The use of different reward functions and environment settings allows for a comprehensive evaluation of the algorithm's performance and robustness. The fitted hyperparameters for the baseline algorithms provide a starting point for evaluating the performance of reinforcement learning algorithms in the NAVIX environments. The online availability of the hyperparameter settings allows for easy replication and comparison of results. Overall, the paper provides a detailed description of the NAVIX environments and baseline algorithms, setting the stage for a thorough evaluation of reinforcement learning algorithms in navigation tasks.